So binomial radical expressions. First thing we're going to do is we're going to do a little bit of addition and subtraction. And then we'll do some multiplication, and that will lead us right into the division part of it. Okay. So just like when we were doing the multiplication yesterday with monomials, with binomials, it's still the same thing. Your radicands, the indexes have to be the same. So same thing with addition and subtraction. Index must be the same. So that's kind of, again, that's not really a step. It's more of just a check. Okay. The other thing that's got to be the same when you're doing addition and subtraction are the radicands. What's on the inside has to be the same.
If these were to be the same, is it undefined or is it like?
We're getting there. Just hold that thought for a second. So again, if you think about what we're doing yesterday, this was our index and this is our radicand. So first off, index has got to be the same. Now, if the indexes are different, you're done. Everything else is after that. Radicands must be the same. If the radicands are different, though, we'll talk about what we'll do after that. And then once the radicands are the same, you're either going to add or subtract coefficients. Again, your coefficients would be whatever's out in front of the radical part up there. Okay, now here's the big thing with this one. Don't change the radicand. That you've got to think about when you're adding, subtracting. Think like when you were doing just variables. That if you do 2x squared plus 3x squared, what happens if you do 2x squared plus 3x squared? What's the answer? 5x squared. Did you change anything with the variable? No. Same thing with radicands. If you're going to do, 2 squared of x plus 3 squared of x, you still just add the numbers in front, and then you don't change the variable. Don't change the radicand. So the only thing that's different is everything we've done before, we had exponents that were positive, that were just whole numbers. Now we're looking at radicals with different things. And so on that part of it, you're not going to change the radicals. Okay, so let's give you some of these first, make sure everybody's okay with it. And then we'll talk about the next little thing we got, because that's like the halfway point with adding and subtracting, and then we'll show you the second part of it here in just a minute. All right, so for example, A, let's go 7 third root of 5 minus 4 third root of 5. All right, index 3 here, index 3 here, so the indexes are the same. The radicands, square root of 5, or third root of 5, third root of 5, so we're good there. So from that point, we're just going to do 7 minus 4. So that's 3, third root of 5. Okay, so if you had, let's say, 8 square root of x minus or plus 9 square root of y, both square roots, so the index is 2 for these. The radicands are different, so if they gave you one like this, you would just say that it's already simplified. because your radicands are different. There's no way to break them down. So in that case, it's just done. That's it. That's all you can do. All right, so let's say we've got 3x squared of xy plus 15x squared of xy, and ask you to simplify that one. Again, indexes are both the same because they're both square roots. You've got xy on the inside for both radicands, so you're good there. Again, from that point, you're just going to do 3x plus 15x, which is 18x. And again, you do not change the radicand. It stays just like it is.
Why would it not be 18x squared? If there's 1x plus 1. You're not.
Oh, yeah. Remember, multiplying is when you add your exponents. If it's addition, you just add, subtract the numbers. Okay. Now, and I know somebody's thinking, well, that seems really easy. Is there more to it than that? Well, of course there's going to be more to it than that. All right, so here's the other part. If the radicands are different, because I doubt that you're going to see anywhere the index is going to be different from one to the next one, just because, again, if the indexes are different, if one's a square root and one's a third root, there's nothing at all you can do to it. You just go, oh, we're done. So if the radicands are different, you have to simplify the radicands if possible. And then add or subtract. Because again, it's not going to be as easy as now. You'll get a few where in the beginning it'll kind of go through this one, but most of these, your radicands are going to be different, and you're going to have to take the radicands and you're going to have to break them down to simplify them to get to what we're doing. So this is third day in a row where we're still working on simplifying, working on the radicands and breaking them down. So that's obviously something pretty big at this point. All right, let's keep it really simple for this one. I said square root of 12 plus square root of 3. So again, index, they're both square roots, so the index is good. The radicands are different. So basically now we're going to say, all right, if the radicands are different, simplify the radicands if it's possible. Back up here, if we go back to this one, where we were, these radicands were different, but there's nothing you can do to simplify square root of x or square root of y. So there's nothing you can do there. Square root of 12, square root of 3, you could take square root of 12 and break it down, right? If you start thinking about 12, that's 4 times 3. And the square root of 4 is? Yeah, that's just 2, right? So that's 2 square root of 3 plus square root of 3. And now you've got it so that the radicands are the same. So now you can combine the coefficients. Now, one thing you got to remember for this one, if it's square root of 3, what coefficient's understood there? There's a 1 there, right? Because this is 2 square root of 3. This is really technically 1 square root of 3. So if you combine this thing together, that would be 3 square root of 3. Okay, so radicands are different, obviously. Break them down until you get them the same, and then once they're the same, then you combine, add, subtract the coefficients that's in front of your radicals. It's the same. All right, so let's crank it up a little bit. Let's do third root of 250 minus third root of 16. All right. And we've kind of learned that you can't always depend on your calculators because your calculators will not always give you the answers that you're looking for. Sometimes they do, sometimes they don't. So for these, we've got to break down the numbers because obviously the numbers are something on those we can break down. I'm going to go ladder method on this one. So with 250, it's even, so I'm going to divide it by 2. 125, I can divide it by 5. And then 25, you can divide it by 5. Right at the bottom of the paper, so let's put that one here. Okay, so that one would be third root of 2 times 5 times 5 times 5. Let's go ahead and break down the 16 as well. It's even, so let's divide it by 2. 8 divided by 2, 4 becomes 2 times 2. Okay, so 250 is 2 times 5 times 5 times 5. 16 is 2 times 2 times 2. It's 2 to the fourth power, basically, if you look at it that way. And what we were working on yesterday was this one index is 3. So we're looking for groups of 3. There's 3 5s, so that 5 will get out. The 2 doesn't have enough buddies, so it will stay on the inside. We've got 4 2s, so we can take 3 of them out. Again, we're left with 1 that's there. So now we're left with 5 third root of 2 minus 2 third root of 2. Now the indexes are obviously the same, but the radicands are the same now. So basically then we can make this thing out to be 5 minus 2, which would be 3 third root of 2. All right, and that's more of the problems that you're going to get you're going to get a problem. You're not going to have anything that you can combine like terms, and you're going to have to break them down some way or another to kind of make it work out to be what you need to be. If you happen to have 3 terms, there may be 2 that you can break down and combine together, and there may be 1 that may just be kind of stuck by itself. So it just depends on the numbers and how they're set up and how they match up there. Okay. Everybody all right there so far? Okay, so that's your options with, again, if you have more terms, you just have to break another one. I mean, again, we could do it with 3 or 4 terms, but it's the same thing. You just take each term, break it down as much as you can, simplify as much as possible, and then when you get to the end, any of them that have the same radicand, same index, that's where you can start basically doing your addition and subtraction there. All right, now for multiplying. And we did do multiplying yesterday, but today we're going to do multiplying, not just one term, but 2 terms. So we're doing binomials. And this is everybody's favorite thing to do, which is really not bad. Y'all complain about this, but it's really not bad. And you're going to be doing the full method. But instead of using x's and numbers, now you're going to be using square roots and third roots and fourth roots and that kind of stuff. All right, so let's go with this one. Let's go with 3 plus 2 square root of 5 times 2 minus 4, or 2 plus 4 square root of 5. Okay, so this is going to bring back in basically the multiplying that we were doing yesterday. Now, again, you're going to get something that's mixed in, like this part of it. 3 times 2 is 6, so there's nothing there you can really do. This one we're doing 3 times 4 square root of 5. So it's 3 times 4, so that's a 12 square root of 5. For this one, it's 2 square root of 5 times 2, So on the outside, 2 times 2 makes that 4 squared of 5. And then for the last one on the outside, it's 2 times 4 for 8. And then on the inside, 5 times 5 is 25. Because what we were saying yesterday was if you're going to multiply radicals, you multiply the outside numbers, the coefficients, and then you multiply the inside numbers, your radicands. And then once you do that multiplication, then we go back and break it down so we can see what it's going to be. Okay, so the 6 is 6. There's nothing you can do with it. But here's where we use the addition and subtraction, because what is, from the previous problem up here, if it's 12 squared of 5 plus 4 squared of 5. That's 12 plus 4, so that's 16 squared of 5. And then we've got 8 times the square root of 25, but the square root of 25 is just 5. So then 8 times 5 is 40. Which means we've got 6 plus 40, so that would be 46, and then 16 squared of 5. Right now, and which number you put first, it doesn't matter. Whether you put the 46 first or the 16 squared of 5 first, as long as you've got 16 squared of 5 and 46, either way you go there, it's fine. It doesn't matter which one's which there. All right. So again, either one of those, it does. This one, there is no standard form for these. So whether you put this or this, it does not matter because either answer is correct. All right. Everybody all right? Is that freaking anybody out? Is everybody okay?
So why do you do plus 8 times 5?
Oh, so we've got square root of 25, right? So square root of 25 is 5. So that's really 8 times 5. So that makes that part out to be 40. So if you inside your any radicands you've got, you still go ahead and break those down as much as you can. Okay. All right, so let's go another here. Throw a few more square roots at you on this one. All right, so let's go with 5 square root of 2 minus 4 square root of 3 times 6 square root of 2 plus 7 square root of 3. Make it so we got all radicals all over the place. Okay, and again, just full method on this thing. So it's 5 square root of 2 times 6 square root of 2. So on the outside, 5 times 6 is 30. On the inside, 2 times 2 is 4. 5 times 7 is 35. On the inside, 2 times 3 is 6. Wait, no. Yeah. I was looking ahead and thought I had something wrong, but we're good. All right, for the next step, we've got 4 times 6. It's negative 4 times 6. Let's say negative 24. 3 times 2 is square root of 6. And then negative 4 times 7 is negative 28. 3 times 3 is 9. Yeah. Now, a lot of simplifying we can do here because what is the square root of 4?
2.
All right, so we know that's 2. So that's 30 times 2. So that would be 60. For this one, we've got the same radicands here, so we can do 35 minus 24, which would be 11, square root of 6. Square root of 9 is 3. So it's negative 28 times 3, which is a negative 84. So we've got 60 minus 84. We can put those two terms together. That would make that a negative 24. And we've got the 11 square root of 6 that's there. Or again, if you do the square root of 6 first, you can make it 11 square root of 6 minus 24. Again, either way is correct. There is no standard form like we had with all the other things that we were doing with the imaginary numbers and the polynomials, all the things. This one, it's just give me an answer and we're good there. Okay, now, depending on the numbers sometimes too. The numbers, the terms, the things you have, you may get an answer that might be a little easier than what you think. So let's say we're doing 6 minus square root of 15 and 6 plus square root of 15. Okay, so we do 6 times 6 for 36. We've got 6 times the square root of 15, so it's just going to be 6 square root of 15. Negative square root of 15 times 6. Basically, again, you can think about that as being like a 1 there. So really it's 1 times 6. That's a negative 6 square root of 15. And then negative times positive is a negative. 15 times 15 is 225. All right, so 36 is good. But what happens with 6 minus 6, right? Yeah, so that's like having 6x minus 6x. That's going to be 0 times square root of 15. But if that's 0 times square root of 15, that's just 0, right? It's just gone. So it's 36. And then the square root of 225 is 15. So that's really just 36 minus 15. So the answer is just 21. So depending on the numbers that you pick sometimes, the radicals may just go away and you may be left with just a whole number. It could be that the whole number goes away and you're left with just a radical. So, just depending on how it sets up and where it goes and what it is, the numbers may all be, different just depending on what you've got and what you're going to do. Okay, so expanding the multiplication, yesterday we were doing monomials. If you expand it into binomials, it's still the same thing. It's just after you get finished, you've got some combining like terms where you've got to do some addition and subtraction. So that's why we had to kind of pause for a minute where we were yesterday. It was kind of at a good spot there because we could take, all those terms and things we're doing multiplication and use that to expand the binomials, which then brings in the addition and subtraction, which will kind of lead us into the division part, which is where we're going next. Okay, and with division, still all in the same section, still just basically all operations here. So with division, there's a couple of different ways you can go about division. And really, there's two types of division. You got one where it's asking you to just divide and simplify. Okay, and what makes usually the first one when we're doing this one is it will just say divide, so it'll be really easy. The second one we do it'll be a little easier because they're going to tell you to do something different. And we'll show you that part here in just a second. We'll get to the first one first here. Okay, so they ask you to divide and simplify. Well, it does what it says do. You divide the radicands. Now, sometimes you can do division, but sometimes on these you might have to think fractions. If you've got a fraction, sometimes you can, if it was 100 over 2, and that was your fraction, you could just divide 2 into 100, right? You'd have your number, you would be good to go. If you flip-flop that one, if you had 2 over 100, you're not dividing it, you're just dividing them. I mean, you are, but you're dividing them both by 2 to simplify it. So for these, you've got to think like simplifying fractions, that it may be that you might actually divide the number, the bottom, you may be able to divide the denominator into the top and just simplify it and get 50. But if it's 2 over 100, then you got to think simplifying a fraction that would be 1 over 50. So just realize that the division might be actual division, but it may actually like be simplifying a fraction division too. So we're just dividing both things by the same thing there. Okay. And then if you have variables, multiplication, you add the exponents. So division, you're going to, subtract the exponents. So divide the radicands. Again, think simplifying fractions. Subtract your exponents. And then once you've done all that, then you see if you can do any simplifying after that. Okay, so here we go. Square root of 200 divided by square root of 2. All right, so again, this is kind of more like this one back here that you can think about. And almost, honestly, the way they do a lot of these problems is if they give it to you as 2 separate radicands, go ahead and think about those 2 radicands together. That you've got 200 divided by 2. Well, that one we can divide, right? Just 200 divided by 2, that's 100. If you have a square root of 100, there you go, that's just 10. So to me, it always seemed like that whatever question they give to you, if they give them to you as separate radicands, you put them together and then you break it down. If they give it to you as one big radicand, usually they want you to break it into parts and then simplify each piece of it. So it just depends on how it's written a lot of times. All right, let's do a third root here. We haven't done anything third root wise, so let's throw in something where we're not just doing square roots. Let's do third root of 81 divided by third root of 3. Okay, so if you put them together, it's 81 divided by 3. It's third root of 27. And if we break that down, 27 would be 3 to the third. A lot of 3s, right? So then your exponent, your index cancel each other out. So we'll do third root of 27. That one would be just a 3. Okay, I know somebody's thinking, every time we do this, are we always going to get just a whole number? No. Let's give you one where you've got a mix where you're going to have, I guess where it doesn't work out perfectly, where you got a mix of radical answer, you got a mix of something that gets out, so we just got a bunch of stuff that's here. let's do third root of 250. We'll throw in some variables, x to the 7th and y to the 3rd. And then we'll do third root of 2x squared y. All right, so they're all got a bunch of stuff here. So let's see if we can just make it one big radical, because you got 250 divided by 2. So that's 125. You've got x to the 7th over x squared. We're going to subtract those two exponents, make it x to the 5th. And with the y that's there, remember that technically is y to the 1st. So when you subtract those exponents, that would be y squared. All right, now, and that problem now just becomes a problem like we were doing yesterday, where now you're just going to take this thing and break it down as much as you can. We're going to take it one piece at a time. So if we break it apart into pieces, we've got the third root of 125. For the x's, it's x to the 5 divided by 3. And for the y, it's going to be 2 divided by 3. All right. Again, if you check third root of 125, that one does actually come out to be a nice, neat number. That's just, yeah, it's just 5. So with x to the 5/3, we're going to divide the 3 into 5 to know how many x's we're talking about. 3 going to 5 one time, with 2 left over. And then for the y's, we're going to divide 3 into 2. It won't go. So we got 2 left over. Okay. And then what we were saying yesterday was, when you're doing this with the simplifying with the exponents, with the variables, this tells you how much gets out. This tells us, because it's remainder, it's going to remain on the inside. So this tells us what we're going to have left over on the inside. All right, so the 5 got out. We're going to have one x that gets out and no y's that get out. And then on the inside, we're going to have 2 x's and also 2 y's. All right, second thing we're going to do, and we've already done this. We just got finished with trig, so y'all have done this. I'm absolutely positive, yes. Top 2.
Is this still number 8?
Yep. We're going to rationalize the denominator. All right, and even in this one, there's actually, really technically, I guess 3 variations of this one that you could do. Because there's a different thing you do for square roots versus all the other roots that you do. So we're going to look at, and again, square roots is what we were doing with the trig. That if you remember, if we were doing a problem and your answer was, let's say it was 2 over the square root of 3. Anybody remember?
Yeah.
All right, somebody said, yeah, what do we do?
Take the radical, move it up to the denominator.
Okay. All right, the shortcut was we would take this radical from the denominator, move it up to the top. And on the bottom, you would just write the number without the radical. Now, technically, what we were doing was, and you just, you don't necessarily have to write this down, just kind of watch. But what we were going to do was we were going to take this original problem, whatever was in the radical, you wind up multiplying by that radical that's in the denominator. So then that made that 2 square root of 3 over square root of 9, but then we simplified square root of 9 to make it just 3. So this was our shortcut, was moving this radical to the numerator and then just take the radical off the denominator. Technically, we were multiplying by whatever it was that was in the denominator. Okay, now that works for square roots when we're going through these. So, if we had, so if that's example 1 there. Let's say we had 7 over the square root of 2. Again, we're going to go shortcut on this one. We're going to move the radical from the bottom to the top and leave the radical off of the bottom and just give us the 2.
Will we ever simplify the fraction?
Yeah, so if this had been 7d square root of 2, you'd have 70 square root of 2 over 2. You could take 70 divided by 2 and make it 35 square root of 2. Yeah, so depending on the numbers, you may have to simplify a little bit. If that was just a 7, obviously you wouldn't. But if it was 7d, then you could simplify that thing. Okay, if it's, even if it's an x or something like that, if it was 4 over the square root of x, it would still work the same way, that you would take that square root of x off the bottom, move it to the top, and the bottom would just wind up being an x. Okay, so rationalizing. Again, we just got finished doing that with trig about a week ago. So hopefully that's still kind of fresh in your mind, bouncing around on those because of, how the shortcuts we could do for those, the things we could do. Okay, now here's the part that we didn't do. And here's where it's going to change just a little bit. For any other index that does not equal 2, and the wording on this one's a little, I won't say it's a little weird, but it's just, it's, the wording is a little funny on this one. It's more of, if you see the example, we'll see it. I'll try to give you the best words I can. You multiply the numerator and the denominator. Wish those words were shorter. So for any other index that's not equal to 3rd root, 4th root, 5th root, 6th root, 7th root, you fill in the blank, any index other than 2. You're going to have to multiply the numerator and the denominator. By the radical with a power of the radicand needed. Again, the wording is terrible on this one, so I apologize. I'm just a math teacher, I'm not an English major. So needed to cancel the index, or the same as the index. Well, let's just say to be the same as. That might be a better way of saying that. So we're going to multiply by power the radicand whatever's needed to be the same as the index. And again, the wording, I apologize at the time because the wording on this one's terrible. Because I can't really find a better way to say it other than that. The example will make it a lot more clear than my wording, because my words, and I knew this one kind of going in, because the wording is just terrible for that for me. Sometimes I can say things real well. This is one of those where it's like, okay, I never can get the words quite the way they want to. All right, so here we go. So let's say we're doing 10 over the 7th root of x squared. All right, and if it was square root, we just took this thing, moved it up top, and then we just cancel out the bottom. But we're not able to do that for this one. So here's what we have to do. All right, this is the 7th root, or the index is 7, right? If we're wanting these things to cancel, everybody okay that we would need the 7th root of x to the 7th? So that way, if we have the 7th root of x to the 7th, these would cancel, we would just get x, right? Okay, so if there's 2 x's here, how many more x's do we need to get to 7? We need 5, right? Just subtract. So basically, you just subtract these two numbers, and whatever that is, that's what you're going to have to multiply by. So if you've got the 7th root of x squared, just subtract these two numbers, and that tells you what power the radicand needs to be. And that way on the bottom now, we'd have the 7th root of x to the 7th, because you would just add these two x's to these 5 x's, and that would make it x to the 7th. Those would cancel, because we do 7 divided by 7, which would just be 1. So then our final answer there would be 10, 7th root of x to the 5th over x. Okay, so square roots are a lot easier than 4th root, 5th roots. Fill in the blank root that's not a 2. You just have to kind of think your way through a little bit more. So it's basically always going to be that you're going to subtract the exponents here, and then that's what power you need to put there, so that now you got 7 root and 7th power. The powers, they cancel out, basically just gives you x to the first here, which is what we want. Okay. Basically, you just subtract these two numbers. Subtract your index and your power. And then you multiply that top and bottom. Which is technically, again, if we go back to the technical way we were doing this without the shortcut, same thing. This was square root of 3, so we multiply the top and the bottom by that same number in this case. But this one's a little different because we're trying to make it so that this will cancel and just give us x to the first, so that there is no radical in the bottom. And to do that, we just got to figure out, all right, if we've got 2 here, if we put 5 more in, now we've got a total of 7 on the bottom, and that would cancel out.
So I get that you added the exponent,
Mm-hmm.
but so you never multiply or add the index or anything, you just leave it how it is?
Correct. Yeah. Yeah, because again, the whole thing with the rationalizing part is we don't really care what happens in the numerator. It's all about just getting it so the denominator doesn't have a radical there. So the top's going to look kind of ugly, but that's okay. All right, let's do a couple of those just to make sure everybody's okay. And again, there's not a whole lot of work with these because of how it's set up. So let's go 8 over the 10th root of b to the 3rd. Okay, so again, what we're going to do. And again, once we start to see these, we kind of get it here. Just take these two numbers, take your index and your exponent, and just subtract them. So that's b to the 7th. So we just need that to be a b to the 7th. I'm going to do that on the top and on the bottom because it is a fraction. All right, and here's where you can kind of save your steps a little bit. Because we've got 8 times the 10th root of b to the 7th. On the bottom, we know this is going to be b to the 10th, and then your 10s would cancel. So it's just going to be b. Because if we put these two things together, that gives us the 10th root to be the 10th. But again, if we get that, 10 divided by 10 is just 1. So then we're back to that just being a b. One more of those?
No.
All right. Okay.
It's my first one.
Okay. Let's do this. Let me give you one more with just the variables. Let me sneak in one without any variables. Let's go 12. So let's go 12 over the 18th root of x to the 12th. Now, and some of you may be okay just kind of skipping the work and looking at it and going, oh, well, that means I'm just going to do 18 minus 12, which is 6, right? So you may be good enough that you can go, all right, 18 minus 12, that means I'm going to have to put 6 more on the bottom, which means I'm also going to have to put 6 more on the top. And when I put the 6 more on the bottom, I'll have 18, they'll cancel. And I'll just get x. Okay. So it's almost, you can almost kind of think the same thing we were doing before. The only thing that's going to be different is subtract these two numbers, right? 18 minus 12 is 6. So now you're going to have 6 more on the top. And when you do that, when you put the 6 more on the bottom, they're going to cancel and it's going to leave it with just the x's there. So you can almost do the shortcut here. The only difference is instead of just taking this thing and moving it to the top, you got to subtract these two numbers and put that on the inside. Same thing here. You had 10 minus 3. We're going to put 7 on the top. We're going to take the radical off the bottom. So you can go ahead and make a little bit of a shortcut here. All right, now, sometimes with the numbers might, I'll give you one more with numbers here. This will be the last one we'll do for the rationalizing. So you've got 4 over the 4th root of 2. All right, now here's the thing that will hopefully kind of help a little bit on this one. There's 1 2 that's there, correct? So we know we need to subtract 4 minus 1, so that means we're going to have 2 to the 3rd. So if we go shortcut on this one, we're going to have the 4th root of 2 to the 3rd up here. And on the bottom, once we put 2 to the 3rd down here, that's going to cancel out, so that would just be a 2 that would be there. Now again, if you need the thoughts of what we're doing there, this is a step that maybe, if you want to skip it, you can. Because we're going to do 4 minus 1, we need 2 to the 3rd on the bottom. We also need 2 to the 3rd on top. On the bottom now we've got 2 to the 4th, but it's the 4th root, so those cancel and give us 2. And we've still got this yucky looking thing on top here. Okay, but what is 4 divided by 2? That's just 2, right? So that's 2, 4th root of, and we got 2 to the 3rd. Looks a little funny like that. So let's just go ahead and do 2 to the 3rd. 2 times 2 is 4. 4 times 2 is 8. So let's make it 2 times the 4th root of 8 for the final answer. All right, one last one here. One last rationalizing. Well, this is the last. That was the last one of that one. Here now we have a different one here. It's a 2-term denominator. Now, and y'all have already actually done this one. Y'all just probably have forgotten about it. So let's go 3 over square root of 6 plus 2. All right, so if it's a two-term denominator, this is why we had to kind of do the multiplication first, and then we kind of put all this all together. If it's a two-term denominator, we're going to take the original problem we've got. Oops, if I can write it correctly. And we're going to multiply the numerator and denominator by the same thing in the denominator, except we're going to change the sign from positive to negative. Anybody remember what that was called? There we go. It was conjugate. Yeah. So if you change the sign, that's conjugate. Only thing you have to remember is the great thing about the conjugate is that it's the full method, but it's really going to be the shortcut is it's going to be the FLA method because the O and the I are going to cancel each other out. So this thing is really just square root of 6 times square root of 6, which is square root of 36, and then minus 2 times 2, which is 4. Now, the top part, I guess we can go ahead and do distributive property. Well, let's just leave it. It's kind of iffy on that one, how you want to go through that one. We'll go ahead and multiply it out. It's 3 square root of 6 minus 6. We might have to go back and reverse it in a little bit, but we'll be okay. All right, so we've got 3 square root of 6 minus 6. That's over. Square root of 36 is 6, right? 6 minus 4 is 2. And this is one of those where they would probably break it up into 2 separate parts because that's 3 square root of 6 over 2 minus 6 over 2. So that's 3 square root of 6 over 2 minus 3. Okay, does that look a lot better? No, not really. But it's what they would say that would be them rationalizing a two-term denominator. Okay, so is that a huge help? No. But it's just what they're asking for in that case.